I would like you to recall how you would have approximated the area underneath this curve x range from A to B. We chose an arbitrary value of x, call it x sub 1 asterisk in that first subinterval to go up to the curve to determine the height of the first approximated rectangle. Then in the second interval, we chose x sub 2 asterisk to be an arbitrary chosen value of x, somewhere between x sub 1 and x sub 2, to go straight up to the curve to determine the height of that approximating rectangle. We did the same thing with this arbitrary I subinterval, and even with the last subinterval. How the x of I asterisk is chosen in each of these subintervals can be different. And so this may have been an approximation. For the area underneath the curve. But to get the exact area, we're simply going to take the limit as n increase unbound. Now, I don't think I did a very good job from a board space, so I am going to erase this. I'm not going to change anything, but give myself a tad bit more room. I just said out loud that this beast right here approximates the area underneath the curve over the interval from A to B. But if I take the limit as n increase up bound, this gives me the exact area underneath the curve. Now, sometimes this pops up in applications quite nicely in dealing with things other than actual area underneath the curve. So if you don't mind, just like with derivatives, I'm going to go away from this idea of looking at a graph. So here I go, a whole new man-made definition. So important, I give it a name. I refer to this as my definite integral. And for now, it merely represents area. I will have an elongated s, sort of like mimicking the uppercase Greek letter S. Or think of that as just the Greek letter S stretched out. Here's my function f coming from here. And I'll follow that with these symbols here. But do not treat that as some kind of differential. And it's not being multiplied to the f of x. It's just a combination of these symbols here and here tell me that I've got an integral. And it's a definite integral because I have what I refer to as a lower and upper bound of integration. Back in grammar school, you used to call that an addend. You used to call that a subtrahend. You used to call that a radicand. So keeping up appearances with that language, I will think of this as my integrand. Now, notice that this definite integral, even though it gives you area, could give you negative area, because technically speaking, the delta x is that large x value minus a small one divided by n, which is always a natural number that's positives. And so if my function lives entirely below the x-axis over some interval from A to B, that's going to give me a negative area. So think of this definite integral as giving you a signed area. Or maybe the curve f partially lives above, partially lives below the x-axis, and it can give you some combination of those positive negative areas. Now, I have to confess, in practice, this is kind of difficult to work with. So in practice, and actually computing actual areas in these curves, I have a tendency to use the right endpoint rule, meaning each and every one of these x of I asterisks is chosen as a right endpoint of those subintervals. So if you don't mind me carefully coming in and maybe describing these x of i's slightly differently. So here I go. First one, I'll revert back to A. The second one, I'll refer to as A plus a small change in the x direction. That's the length of each of these subintervals. I would think of x of 2 as A plus 2 of those lengths. I would think of x of I as A plus I of those lengths. Just to make sure I haven't miscounted, check out how x of n really should be A plus n times my I. Excuse me, I meant to say n times delta x. But that's the same thing as A plus n times b minus a over n. I'll let you clean that up, but that reduces quite nicely down to just a b. So, like I said, rewriting what I have with that definition of definite interval. But using the right endpoint rule to make a decision how I choose each of these x of my asterisk, then what's going to be in the integrand is going to look a little different. So I shouldn't say integrand. How about just saying what's in the sum is going to look different? It'll be my f of a plus my delta x times my delta x. Where? I'm getting too sloppy. Meant to write where my delta x is computed as such. So for a brief while, can we stay away from the theory? Let's just dive in right away and take a peek at an example of evaluating such.